So let's look at the first one. How do you go about working that out, getting the energy? Actually, this is the formula. Mod of the signal squared integrated. All right? And of course, we don't expect you to remember that, right? Remember this best friend that I introduced before, your formula sheet? Energy, power, signals. Formula is there. It's all there. All right? We don't expect you to remember. What would you get? 3. Any other answers? Okay? Majority has it. And that's right, because if I actually substitute and do it, right? Because it's the signal squared. And this is the simplest signal possible, right? I mean, it's got a 1 and a -1. So you square it, it's still 1. But I've shown all the working anyway. What about the next one? The same, right? Because when you square it, you get the same thing. Gets rid of the sign. What about that one? Same? Yes, it is, right? So even though it looks different, and I'm showing you all the working, you don't actually have to do it. In fact, I don't want you to do it. Only maybe for the first one, right? Once you've got the first one, you should know that I don't need to do it anymore, because that's what it will be, right? Between 3 and 5, 1 squared, and between 5 and 6 is -1 squared. Answer will be the same. If you look at it, it's the same signal, just delayed. What does delay mean? It's just I've arbitrarily set a t0 somewhere else. But it's the same signal. Same shape, therefore it has the same energy. All right? So this is one of the things, the questions are designed to show you certain things that you need to know. So it's the same signal, so it doesn't matter even if you negated it, energy will be the same. If you delay it or time shift it, it's the same. What about the next one, though? What have I done with that signal? Sorry? Doubled it, right? So it's gone from 1 to 2, right? And instead of -1, so I've just multiplied the amplitude by 2. What's the answer? 12. 6. Did you work that out or did you guess that? 12 is correct. But how 12? Why 12? Because it's squared. Very good. Right? Amplitude squared. So if you look at what the formula is doing, you're taking it and you're squaring it. So if you double it, it's 4 times. And just to show you that it is correct, we've actually done the working. We try it out, and you'll see the answer is 12. So the magnitude, squaring the magnitude will quadruple the power, right? Squared. Whatever happens to the magnitude is squared. Next one. First one. What do you do there? So let's look at the first question. A. What's the signal? So this is the only thing that you need to think about, right? How do we model the signal with an equation? So what does that look like? What equation would I use? Y equals to x, but is that x there? T. Right? So you just say the equation is just t. Slope of 1, right? If you look at the slope, 1 over 1. So it's a slope of 1, is 0, so it's t. So the equation to model the signal is t between 0 and 1. So if you do that, so that you got to do the integral, which is the same as before, right? Energy function, right? So if it's t, and you square it, what do you get? T squared. Then you integrate that. Yeah. Okay, so that's that. So you get t cubed on 3 between 1 and 0, which gives you a third. All right? So that's a basic integral, which you should know. Answer for the next one. Same. That's what I want. Don't go around doing integrals again. Right? You'd get fired if you were working for me and then sat down and did an integral again. In fact, I normally wouldn't want anyone to do any integrals, but that's beside the point. Right? Okay? It's the same. And the third one? Same. And the fourth one? It should come like that, right? It's the same thing, what I said. Same. Same. But I've just shown the working in case you don't believe me. Right? So obviously, here it's minus t, because it's negative slope. Right? Slope of minus 1 between minus 1 and 0, and that's the same slope of negative 1, so minus. But the answer is the same, right? So this is t minus 1, because it's like t, but delayed by 1, right? Or you can think about it, if I draw the line back, it'll hit at minus 1, so it's like x minus 1, t minus 1, right? But you don't need to do that. The answer will be the same, right? Saves you of having to do this integral and then doing substitute. It's all a waste of time, right? If you know the first one, you know them all. That's where I want you to be at. Okay? And that point. So there's no change for reversal or time shifting or negation. Point to note. What about the next one? Was that a guess or did you do it? Yeah. All right. But what's the equation for the line there? Yeah, 2t, right? If you look at the slope, right? Rise over run, 1 over half. So slope is 2t. And you integrate that. But actually you don't need to, but I'm going to show you 2t. So it becomes all squared, becomes 4t squared, and then you do that. It's 1/6. But what's the point here? What have we done? What have we done with the signal? We've squashed it in time, right? Halved the time. So if you've halved the time, then the energy is halved. If we double the time, the energy is doubled. So in terms of time, the energy is proportional to the time that it takes. Whereas, what about F? Four. How did you get 4? Well, that's correct, right? But you don't need to do the integral because I've doubled the magnitude, so it's 4 times. So if it was 1/3, so what you need to do is, what have we done to the signal? This is the same as that, except I've doubled the magnitude. So same as before. Doesn't matter the shape. If I double the magnitude, it's the exact same shape, but I've doubled. Therefore, it is. So that's time scaling, and that's 4 times, which is amplitude scaling. So time scaling is linearly proportional to the time. Amplitude scaling is that square function, but it comes from this, right? It comes from the x squared. So you don't have to waste your time doing heaps of integrals. As long as you know one base one, that's it. You can work out the rest. Right? And in fact, that's what we do quite often. We will find it, let's do something to get in the simplest form, find the energy, and then work it out. So this question then, now I'll give you a bit of time to try this. It says, determine the energy and the power. And in case you've forgotten, it's in the formula sheet anyway, but I'll put it up there for you. So that's the formula for power. So here you're integrating from minus t on 2 to t on 2, so it's like one period divided by that period. But I say limit as t approaches infinity, right? What's the energy? Infinity. So do the rest of you disagree with that? Or is everyone just hedging their bets? Well, it's correct, right? So if you had actually looked at the slides and listened to the lecture, right? If you have a periodic signal like this, why is it infinity? It's infinity because it goes on forever, right? It's periodic, and essentially goes on forever. So if I'm going to square it and integrate it, it's going to be infinity. So you actually don't even need to do any work. You just say, well, it's periodic with t equal to 4, but energy will be infinite because it's periodic. It's not time limited. So, which is why we can't find the energy of a periodic signal, we find the power. In other words, it's averaged over that period. So, did anyone get an answer for the power? 60 over, well, we have consensus. So, what do? Right? So you apply that, but you look at the period, right? So what we do is, you see, this signal is modeled that way. So it's following the t cube curve between -2 and 2, and then it's just replicated. So we take that, right? -2 to 2, t cube is the formula that represents it, that models it. So you take that, square it, I get t to the 6th, and then integrate that. Okay, so the other part of the question, so remember this, if it's a periodic signal, energy is infinity, you find the power. Now, if I do, it says, what about minus xt? What should the answer be? The same, right? Same as before. If I do a negative because of the square, it's the same. 2xt times it by 4. I double the amplitude. Same thing, right? If I put 2xt in there and square it, I get 4 times. So you can do it the long way. And I've actually shown that. And then that, right? I put it as, right? Double that. But you don't really need to. You just need to know that, hey, it will be 4 times because I've doubled the magnitude. Right? So if I have kx, it will just be k squared, which is that part. Right? So 64 and 7 times k squared. So these are some of the general principles you need to know. So if we have a periodic signal, energy is infinite, we find the power. What about the earlier one? Those ones. What would the power be? 0. Why? Well, there is. What's the period? It's not we consider the period to be infinity, right? An infinite period because it doesn't repeat, right? So then, if you've got a 1 on t, 0, right? So it's averaged over all time, and it doesn't repeat. That's all there is. And you're going to spread it out over all time. You get nothing. So, non-periodic signal, right, or what do you call a time-limited signal, is what we call an energy signal. In other words, it's got 0 power, but it's got a finite energy. Whereas these kinds of periodic signals are what we call power signals. Think about your AC power, right? It's like a sinusoid and stuff, right? Goes on forever. So those are called power signals. Why? Because energy is infinite, you get a finite power. So if you listen to the lecture, you should know that. So I was talking about sinusoids. So first, let's do the first one. Try the first one. Did anyone get this one? 1, 2. Was it easy? Sorry? A bit tricky. He thinks it's easy. Probably got a maths quiz up there. What's your answer? Same. C squared on 2. Well, I'll put you guys out of your misery, right? That is correct. But how? Let's have a quick look. Right, same function. So, think about it. I'm trying to find the power. So, I square that, so I get c squared cos squared. Right? Now, for those of you who remember your maths, that's too difficult to integrate, so we use these usual trigonometric substitutions. So we use this identity, cos squared equals to 1 plus cos 2x on 2, because that is something that we can integrate. So that's what it becomes, 1 plus cos 2 omega naught t plus 2 theta, right? Which then I can separate it out, right? So I've got an integral of 1 and an integral of cos omega naught. Now, when I integrate 1, what am I going to get? T, right? And when you substitute the thing, so I'm going to get T on 2 minus T on 2. I'm just going to get T. And the T will cancel with the other T. C squared. But what about the cos 2 omega naught? If I integrate that, see, I'm going between T on 2 and minus T on 2 and T on 2, right? This is 2 omega naught. So essentially, I'm integrating over 2 cycles. But what am I integrating? If I integrate that, what's the integral? Yeah, but I mean, if you look at that area under, you'll have positive and negative, it'll end up being 0, because I got 2 full cycles, right? And that's what it ends up being. And at the end of the day, this is what we want you to remember, this point. Don't waste your time trying to do those horrible integrals. That's the mathematician's job. The engineer's job is to use that result. All right? We just use that. So if you have a sinusoid, whether it's cosine or sine, it doesn't matter. The power will just be the amplitude squared on 2, regardless of frequency or phase. See, we had a general frequency and a general phase, right? But we had no omega naught term in there, we had no theta term in there. We just got c squared on 2. It only depends on the amplitude. Okay? So given that, find the answer to the other two. That should be a lot easier. For B, what's the answer? 75. Do you have an answer? 75. Anyone want to go up against them? We've got the two maths wizards here. Any other answers? No, they're not. Yeah, it is 75. See, if we look at the 10 cos, right? Just use this. C squared on 2. So you got 100 on 2, 50. What about the constant? If you think about it, if you try a constant, it's just 5, and you do the integral, which I'm showing here. Well, I didn't actually show it to you. But it's just going to be 5 squared. Because it's going to be a constant and just be 5 squared. Averaged out, because you're squaring it, and then averaging it out, it's just going to be 5 squared. Because of the squaring. Right? xt squared. So it's just going to be 5 squared. So a constant value will just be the value squared. A sinusoid will be the amplitude squared on 2. And given that, part C should be trivial. Anybody else got an answer except for these two guys? Part C, yes? Yeah. 178. Anybody else? Well, that's correct. Okay? Because all you need to do is, well, I've got two sinusoids. Doesn't matter what the frequency, doesn't matter what the phase. 10 squared on 2 plus 16 squared on 2. I don't need to think about anything else. Done. All right? So this is the reason why these questions have been given. So you actually get to know these shortcuts and understand them. Not because I want to torture you with integrals. No. In fact, I'm trying to lead you away from that. Use them where needed, but there's all these other shortcuts which you need to know. Now, next what we're going to go on to is this, which is the shifting and scaling of signals like this, right? So, looking at that, I know there are some people who have a bit of issue visualizing this. So, what's the answer to A? Anybody? What does that do? Well, not 4 steps, but 4 seconds. We've got time. So 4 seconds. So it's delayed by 4 seconds. We say t minus 4. So in other words, the whole thing gets shifted to the right by 4. So what was at minus 4 ends up at 0. What was at 0 ends up at 4. What was at 2 will end up at 6. It's just delayed by 4, right? T delayed by 4. So that's it. Right? So for this signal, if you know those 3 important points, you can just draw it. Okay? What about the next one, b? T over 1.5. What does that do? So you're saying it compresses it. We have descent. He says he compresses it. He says it makes it longer. In other words, it expands it. Which one is it? You are dividing by 1.5. Now, normally when you divide, it becomes smaller, right? Opposite. It's always the opposite, right? Because when you divide, in other words, it's taking longer to get there. So it's actually expanding it in time by 1.5. Remember the earlier one? Remember it was 2t when you halved the time, right? The slope became double, so t became 2t. So when you halve it, you times 2, you're compressing it in time. When you're dividing, you're expanding it in time. So you're expanding it by 1.5. So 0 will stay at 0, minus 4 will go to minus 6, 2 will go to 3. And therefore, that. Make sense? So I want you guys to get to know this. You should become part, because this is basic stuff, right? We're going to be throwing you stuff like this, and we'll expect you to know this is what happens. And if you can't visualize it, you can't understand it, you'll be like, what are they talking about? Okay? Especially this, and then in the next slide, or 2 slides after, right? Okay. Next one, x minus t. What does that do? Yeah, it flips it, or it reflects it on the y-axis, right? Positive becomes negative, negative becomes... So the 2 will go to minus 2, the 4 will go to... minus 4 will go to 4. It just gets flipped. All right? Or reflected in the y-axis. And the next one, which is 2t minus 4. Now what do you do with this one? I emphasize this a lot. If you watch the lecture, I spend some time doing this because it's quite important. Yeah. See, in normal maths, if you do 2t minus 4, you do the multiplication first and then subtract, right? But remember, when you're doing time domain, everything is opposite. We're living in sort of opposite world, right? So you do the subtraction first. You do the shift, and then you do the scale, the multiplication. Right? Shift and scale. That's what I emphasize in there. I put a little box, shift and scale. So the minus 4 shifts it. So it shifts it by 4. In fact, we got it here, right? This one, A, that's t minus. So you'll actually get this. The shifting will get you that. And then 2 times 2, 2t. What does that do? Yeah, that means it compresses it by a half. So everything will get... So 0 stays the same. What was it? 4 will go to 2. What is it? 6 will go to 3. Right? You get that. Compressed. You guys getting the hang of it now? Yeah? All right. It's important that you do. All right? And what about that one? What's that doing? So the key is this, right? It tends to throw everyone. What is that? 2 minus t. What? But when you say 2 minus t is just simply the same as minus t plus 2, correct? See, you think about it that way. So you can shift it back by 2 and then flip it, right? So it moves that way and then you flip and you get that, right? Or as actually pointed out by someone in the last class, it's this x minus t delayed by 2, right? So this shifted across 2. Same thing. Yeah? since we already had minus t. Yeah. Okay? Does that make sense? All right. But yeah, we always do the shift first, then the other thing. So you do the shift by 2, and then you flip. Okay? Now, so that's one thing with some generic thing. Now, we will also, that's also important. Why is that used? Where is that used? This shifting and all of that, we use it with these standard sort of basic functions, unit functions. So what is U? Unit step, right? So U is the unit step. Okay? So UT means 0 before time 0, 1 after time. This is one of the most important signals because you're going to see it all over the place. And these questions are going to lead you through how it's used. So let's look at the first one. What's ut minus 5 minus ut minus 7? What does that do? Do you all understand what he said? No? Okay, I'll show you. First of all, like I'm just going to show you how it's, right? What's ut minus 5 look like? So remember, it's the unit step. Minus 5 means it's delayed by 5, right? So it steps up at 5. So it's 0 there. At 5, it goes up to 1. What's t minus 7? ut minus 7. Same thing, but it steps up at 7. So when I subtract one from the other, visualize that, even if I've drawn that, right? I get the first one, which is a step up at 5, but when I minus, so until time 7, I subtract 0. Then at time 7, I subtract 1. So what does it become? 0. So you end up with this, like a pulse, rectangular pulse. You're going to see this time and time and time again. It is one of the most important things. All right? So think of it as a step up, switch on, step down, switch off. And that's a very important concept, actually. All right? So this is how we would represent. So if we had a rectangular pulse like this, we don't have to say, oh, function x define. No, we will just write it like that. We will write it as ut minus 5 minus ut minus 7. And you're supposed to know what that means. Okay? This is a basic concept that you need to know. All right. What's the next one? I add them together. What will it look like? So you go up at 5, then you're adding it, so it goes up another 1 to 2 at 7, right? Just add the two signals together, right? Okay. What about this one then? So here's a hint. You look at it at two separate things. What are you doing, right? There's a multiplication there. If you look at the bracket, there's a ut minus 1 minus ut minus 2 multiplied by t squared. That's a hint. Think about it, see if you can sketch it. You need to be able to visualize these things. Sorry? 2 to 4. No. He actually gave the right answer, but nobody heard him. So what's ut minus 1 minus ut minus 2? So basically, what that is what we've seen before, right? It's 1 from 1 to 2, right? And 0 everywhere else. And you've got you're multiplying it by a t squared function. So what are you doing? Well, wherever it's 0, you're going to cut it off, right? All up till time 1 is multiplied by 0, so it's gone. After time 2, it's also multiplied by 0, so I'm only left with this part between 1 and 2. So that's what you get. So you get the t squared function, and what the ut minus 1 t minus 2 is like what we call, it's like a gating function, right? It switches it on at time 1 and switches it off at time 2 and 0 everywhere else. So t squared at 1 is 1, t squared at 2 is 4, and that's it. So I got the t squared function, but I've windowed it, right? In fact, the term that we use is a window. in time to come, we call it's a windowing function. So you've got that rectangular window. Right? Doesn't do anything because it's 1, so just lets it in between and 0 everywhere else. Okay? So that said, what will D look like? Okay, good. So what he said was if you think about t and then you shift it by 4, right? Or you can think about it as t minus 4. Think about a line y equals x minus 4. Straight line, right? That's what t minus 4 is. So it's a straight line that will hit the x-axis at 4, slope of 1. But what's going to happen, the second part is t minus 2, t minus 4. That means 0 before 2, 0 after 4, only in between. And that's it. All right? So my t minus 4 essentially will be this, right? That's a normal straight line, slope of 1, t minus 4. But I'm just going to go between 2 and 4. That's all I'm seeing. Everywhere else is 0. Understood? Because that's what the ut minus 2 minus ut minus 4. And this is important because we will do this chopping for signals, right? We will always use ut, u, all of that. So we say it's only between this point and that point. That's why I'm giving you this, because you need to know that. All right? Now the next part is using another function, which is the delta function. So what does the delta function do? What's a delta? Just delta t. What's delta t? An impulse, right? A delta t essentially is at time 0, I've got this infinitely high pulse, 0 everywhere else, area of 1. So in the lecture, that's what it is, right? That's what it is, delta t. When it's not, except for time 0, and in other words, whatever's inside the bracket or the parentheses, when that is 0, it's infinitely high. Everywhere else, it's 0, right? So what actually happens? In other words, I'm multiplying with 0 everywhere except that time when the impulse is there. So everything else gets zeroed, and I'm left with that one thing. Because this is an infinitely high thing. But what the second line here is saying, I actually end up with the value of that function. So if I've got a delta that is shifted by time capital T, 0 everywhere except at that, and I actually just get the value of that. In fact, that's something called a sampling function. We will see it much more in week 8, right? So in other words, I'm just looking at it at that point. I actually just get a spike with the height of the function x value at t, right? So if I do it for the first one, when is it non-zero? When t is 0. So basically, I substitute t equals to 0 in there. So sine 0, 0, right? So sine 0 and 0 equals 2, which is just 0, right? But what about the next one? When will it be non-zero? When will that be non-zero? When will I see something? No? You see, it's when whatever is inside here is equals to 0, right? So in other words, when 1 minus t equals to 0. So what will the value of t be? T equals to 1. Right? So I sub in 1 into it. So I'll have sine pi into 1 minus 2 over 1 squared plus 4. And then I get the value of that, which will just be 1 minus 1.5. But I still have to put the delta, though. If I just put minus 1.5 is wrong, because minus 1.5 is a constant over all time. I'm saying 1.5 at that point. Right? So minus 1.5 delta t minus 1. So I've swapped it around from 1 minus t to t minus 1, right? It's a more standard form. Does that make sense? All right? And in fact, I've put this is a bit ahead of time, but this is actually from week 8. So if you look at it, so if I have, basically what it means is if I have some function, if I have an impulse here and I multiply it with that, I will just get the value of that function at that point. If I multiply this impulse with that, I'll get the value at that point. Everywhere else is going to be 0. So in this case, it's an impulse train. I've got all of these, so I'll just get those. So this is what we mean by sampling. Week 8. All right? Okay. So what will we do for that one? Very quickly. What value would you... So now instead of t, we've got omega. So it's a function in omega. This is something you'll see later on in frequency. But the concept's the same. Where will it be non-zero? Omega 0. So what I do is I sub in omega equals to 0, which I get 2 over 9 delta omega, which tells me it has that value at time 0, 0 everywhere else. So if I want to draw it, right, for example, this will be at time 1, right, it's at time 1, it'll be a minus 1 over 5 there. And this one will be at 0, I'll have a 2 over 9 impulse. Okay? And the next one, what would you sub in? Minus 3, right? So you sub in omega equals to minus 3, and that's what you get. Okay? Now, last question. Sorry, I know we started late, so I'm rushing to finish. What about this? All right? So here we've got discrete. So this is what happens when you've already sampled something. We've only got impulses, right? Now, you've got x, that's xn. What's x2n? Now, the thing about discrete, the important point to note is n can only be an integer. You can't have x of a half or 1.5 or 1.1 or anything like that. It's just 0, 1, 2 or minus 1, minus 2, right? Integer values only. Okay? So, in that case, what's going to happen? So, if this is xn, right? So, when it's 0, I'm going to have x0, no problem. When n is 1, what am I going to get? It's going to be the same as x2, which is this. When n is 2, it will be the same as x4, which is already 0. Minus 1 is going to be minus 2. Minus 2 will go to minus 4 here. So in other words, I'm going to get every second sample. If you think about it, what do we learn? Multiply by 2 is compression, right? So I'm going to bring it together. So essentially, I will have that xn at 0, a half, 1, 1.5. But what did I just say? You can't have a half or 1.5. So those, what was at 1 will move to a half and disappear. What was at 3 will move to 1.5 and therefore disappear because it's non-integer value. So this is what we call downsampling. You lose samples. When you compress it, it's gone. Which is why when you compress a picture or you compress a sound digitally, the quality goes down, right? Most of the time. Okay? Because when you do downsampling, you actually do that. You drop half of it. Okay? So the answer will be that. Every alternate. So what was it? 2 moves to 1. Minus 2 moves to minus 1. What was it? 4, which is 0, and all that. That's all 0. Right? 3n minus 1 is the next one. So if you think about it, from what we learned before, same things apply. So minus 1 means it shifts across by 1. And then what do? We take every third sample. So in other words, I will actually get the minus 1 sample, the 2 sample, and then I'll get minus 4 there. So it's going to look like that. All right? I'll shift it by 1 and then take every third sample. This times 3, right? All the other ones will disappear. Does that make sense? So this is the thing to note. In discrete, when you do compression, you tend to lose values. Okay, what about this one? Now we are taking y, which is the lower one there. Y 1 minus n. So what are we doing there? Remember 1 minus n, I can rewrite it as minus n plus 1, correct? So what is plus 1? I shift it to the left by 1. What does the minus do? Come on, guys, those over here. What does the minus do? Yeah, mirror image, right? It flips it on the y-axis. So it ends up being that, right? So the 1 that was at y1 will go to the 0, and the 0 will go to minus 1, and then when I flip, it goes the other way. Right? So I got 0 at 1. Follow? So you see the concepts, and you need to be able to, what's happening with this? We need to be able to visualize it and work through it very fast. Hence the practice. What about the next one? What does that do? Yeah, shift it to the right by 2. What are you doing to y? Same, shift it to the right by 2, and then we add them up. All right? So essentially, what was at the minus 2's will be at 0, and then we're just adding up the two signals and then shifting them, or shifting them and adding them up. Comes to the same thing. So this is what you get when you add them, right? So there, that point there, 0 plus minus 1, that is a minus 3 plus minus 1, will give you a 2, right? So on and so forth. Just adding them. Add each value. The thing about discrete is easy to do because they're specific values, not like the continuous. It's harder. Okay? And the last one, what would that be? What are we doing there? Yes? You're showing something with your hand? Yeah. So x minus n means you flip it, right? But if you look at x, it's an even function, right? If I flip it, it's going to look the same, right? Whereas we're also flipping y. So if I flip y, then the 1's are going to go to the negative side, and the minus 1's are going to go to the positive side. And then what am I doing? Multiplying. So in other words, the ones on the left will be multiplied by 1, the ones on the right will be multiplied by minus 1, and I end up with that. You can try it, each value. You can work it out. But that's okay. You guys follow? So this is what you need to understand and work through, because we will do some weird and wonderful stuff with the signals this way. Right? You need to know what happens when you shift and compress and scale and all right? Especially the part about the UTs and all of that. That's very, very important. It's going to come everywhere. So this is just laying some of that groundwork. Even the thing about sinusoids and the power. Right? All right, any questions? I'll see you next week, but please try and at least attempt the questions before coming. Thank you. See you guys next week.